Hello and welcome to SAS Programming Course Section 7, Part B. In Part A, we ended up with this table when we were looking into calculating descriptive statistics from an individual numeric variable. And we saw that we might want to make some improvements here, and let's jump right into that. So in the last output, we maybe wanted to change few of the descriptive statistics, so we wanted to add some and maybe leave out some. So the way we can do that is that in the proc mean statement we can list the keywords and request specific descriptive statistics using those keywords. You can find from SAS help a more thorough list on keywords available. But we have here chosen mean, median, standard deviation, and quartile range. In addition, we had too many decimal places in the previous table, so here we have requested with this max dec equals 0 that we would present the descriptive statistics without any decimal places. And when we run this code, this is the output we get from this one. Also, the same descriptive statistics, they can also be produced with another procedure called proc univariate. Output will be in very different format when we use proc univariate because it's mainly meant for exploring the distribution of your variable, for example, before going into statistical procedures or so on. In this one, we can also use normal and plot options. Normal gives us tests of normality, and plots or a plot gives us plots to examine the distribution. So we get box plots and histograms, for example. And plots in general, they are often worth looking into because they give us a good overview of the distribution at one glance. So you might find some details that you would miss by just using only the descriptive statistics. But here is the basic syntax with the proc univariate. We give the data we use and normal and plot options here. And in a similar way than in proc means, we specify that in the var statement that yield is the variable we are interested in. And this is how the output looks like. There is a lot of information here. There is first a table of moments giving a different kinds of descriptive statistics showing different properties of the distribution. Then we have the basic statistical measures giving us on the left column, there's a statistics describing the location of the distribution, and then on the right column, statistics describing the variability of the distribution. Then we have simple tests for location, which are not useful here, but they are testing whether the whether the mu equals 0. So, for example, the student's t-test is testing whether the mean of the distribution is equal to 0, which is not really meaningful test here. But in some cases, that's where you would get the one sample simple tests. Then we have tests for normality, 4 different options here. And the interpretation goes so that when there is a high p-value larger than 0.05, then we do not have evidence that the observed distribution would be different from normal. So this gives us indication that the that the observed distribution might be coming from normal distribution. So looking good if we would be interested in assuming normality. Then there's also table of different quantiles. And on the next page, we see that we get also a listing of 5 lowest and 5 highest observations. So table of extreme observations. And we get a couple of these plots because of the plot option. So we have histogram, a box plot, and also this quantile plot. But overall, this plot maybe is the most clear way of seeing that, okay, the distribution looks quite nice and it looks very normally distributed. So if we are assuming normality, it looks good here. Some details about the box plot. So first of all, usually when we talk about box plots, we actually mean two keys box plot, or that's at least the original version of the box plot. Other names you might hear is just box plot, box and whisker plot, or box and whisker diagram. When we are drawing the box plot, we need information about quartiles, lower quartile, upper quartile, and median. And we also specify these inner and outer limits. Inner limit is a lower quartile minus 1.5 times the interquartile range. And the other, or the upper inner limit is a upper quartile plus 1.5 times the length of the quartile range. And outer limits, they are exactly the same, but here it was 1.5 times the quartile range. Then here it's 3 times the interquartile range. And so next we see how we use these details to draw the box plot. First of all, the lower part of the box is the lower quartile. Median gets the line here. Mean usually is presented with some symbol like the plus here, and upper quartile is the other end of the box. Then the whisker here. The way that is drawn, that we first check where is this inner upper limit, which was this one here. So Q3 plus 1.5 times the quartile range, and quartile range is actually the length of the box. So 1.5 times the length of the box is here, and we then draw the whisker so that it reaches the largest observation that is still smaller than the inner upper limit. And then on the other hand, we check where is the 3 times interquartile range. It's here, and we in at least in the original two-case box plot, we use a different symbol for the values that fall in this interval, and then those ones who are larger than the outer upper limit. So the ones that are here, they would be extreme outliers with a different symbol, and then these are just outliers or mild outliers that are here in this interval. And in this case, the minimum is then where this lower whisker is drawn, because there are no outliers at the low end in this case, where the distribution actually seems to be positively skewed. Yeah, then we jump into comparing the distribution of a numerical variable in different groups. So basically we are doing much of the same as we did in the previous part 7.2, but we do it in subgroups. And here we start so that we actually draw a scatter plot to sort of visualize what we have. So we are now looking at the same data experiment, and we want to draw a separate panel for each location, and we want to draw a scatter plot where the x-axis variable is the fertilizer and y-axis variable is yield. And we want the column axis to be discrete. So this is what we get with that. We have 3 different fertilizers, we have 2 different locations, we have 2 panels, so we have 6 groups altogether. And on the y-axis we have yield. So when we have this kind of small experimental data, it might be worth to just draw the whole data into a scatter plot like this, because we can then sort of see that okay, it seems that maybe in location 1 these might be on average a little higher than these, and then here it seems to be a little bit more variation in this fertilizer tree group. Then on the other location, it seems that the overall level is maybe a little lower if we compare to location 1. And here maybe fertilizer 1 is lowest, 2 is maybe a little higher, 3 is about the same, but not so clear to see the fine details on the level. So we might also want to use other tools to examine this further. Sometimes also for further use, it's convenient to form one variable combining all the combinations of 2 grouping variables, and this we can do in the data step. And I think we also saw this already actually in the section 5 of this course. But we just define that if location is 1 and fertilizer is 1, then this new variable location underscore fertilizer is 1. So basically we just list all the possible combinations and give the values from 1 to 6 to the new variable. And then we can also then use this variable to make the same plot in a little bit different way. Now we can just use sgplot. We don't have to use the paneled version, and we just have one grouping variable in the x option, which is this location underscore fertilizer, and then we have the same yield as the y variable, and the image would look like this. So another way to do the basically the same output.